Section: Introduction. In this section, we delve into the dynamics of sparsity in deep networks, particularly focusing on the activation patterns of two-layer MLPs within a standard transformer block. Our aim is to understand how sparsity changes during training, both at the level of individual tokens and across sequences or batches. We observe that sparsity levels and their evolution vary significantly based on the layer index, with the first and final layers exhibiting distinct sparsity behaviors. Interestingly, the activation patterns at the token, sequence, and batch levels often show opposite trends, with layers that activate fewer hidden units per token tending to use more units over a sequence or batch. During training, many hidden units remain inactive, especially in the initial layer of the network. This phenomenon, known as neuron death, varies across layers, with some gaining neurons while others lose them. Neuron death seems to be linked to learning dynamics rather than random occurrences. Although most unused hidden units deactivate during training, a small fraction, approximately 5% of the total hidden dimension per layer, remain inactive from the start. This suggests that optimizing the initialization process for ReLU transformers could lead to better utilization of MLP hidden dimensions, although this hypothesis requires further investigation. Moving on to the methodology, we highlight the importance of multi-layer perceptrons, MLPs, within transformer blocks for learning and storing information in modern language models. Previous studies have shown that MLPs using ReLU activation functions tend to exhibit sparsity in their activations. Our work extends this by examining sparsity metrics at the sequence and batch levels, which are crucial for understanding computational efficiency and the information learned by the models. To quantify sparsity, we introduce three core metrics: per token hidden unit use, per sequence hidden unit use, and per batch hidden unit use. These metrics measure the number of active hidden units post-ReLU at different levels, token, sequence, and batch, and are calculated independently for each layer in the network. Additionally, we compute percentile metrics to analyze how frequently hidden units are utilized within a sequence. These metrics provide insights into the utilization of hidden units during training. Our experiments are conducted with a standard sequence length of 512 tokens and a device batch size of 16, totaling 8,192 tokens per batch. We focus on the early stages of training in our plots, as network behavior stabilizes around 70,000 steps. For a comprehensive view, full plots are available in the appendix alongside the abbreviated versions presented in this section. Section Summary. In this section, we delve into the activation dynamics of two-layer MLPs within a standard transformer block, focusing on the evolution of sparsity during training. We observe distinct sparsity patterns based on layer index, with the first and final layers exhibiting contrasting behaviors. Additionally, we explore the phenomenon of neuron death during training, where some hidden units are never utilized, hinting at the potential for optimizing ReLU transformer initializations for better utilization of MLP hidden dimensions. Section: Model Architecture. In this section, we focus on a 6-layer decoder-only transformer model with a hidden dimension size of 32,768 and ReLU MLP nonlinearity. We trained this model on C4 next token prediction using LeCun normal initialization for the dense kernels within the MLPs and an Atom W optimizer with a cosine decay learning rate schedule. After a warm-up of 5,000 steps, the learning rate peaked at 3E3. We explored how our findings apply to different model depths, hidden dimensions, and learning rates, but all results presented are based on the model described above. Each model was trained on a GCP-TPU v2 slice of type v2 to 32, taking approximately 2.5 days to converge. Our key results show that different layers in the network utilize varying numbers of hidden units during a batch, with a moderate negative correlation between token and batch hidden unit usage. The first layer, layer 0, consistently uses the fewest hidden units, about 13.3%, per batch, while the final layer, layer 5, uses the most, 95.6%. To understand how sparsity evolves during training, we first examined the sparsity characteristics of an untrained model. We observed that higher layers of the network initially use fewer dimensions in the first training batch, indicating a trend towards sparsity induced by the transformations applied by each MLP. Despite some hidden units starting as unused, all layers eventually activate some of these initially dormant units, with higher layers activating more. This suggests that higher layers may benefit from a larger number of hidden units or adapt better to distribution shifts from lower layers. Analyzing the evolution of sparsity during training revealed distinct patterns across layers. Early in training, the fraction of active hidden units per token and the median fraction of tokens using a hidden unit decreased, particularly in the final layers before progressing to lower layers. Interestingly, Layer 0 showed a unique trend of gradually increasing the usage of its hidden units over a sequence, unlike other layers. We investigated when a hidden unit can be considered dead if it remains inactive across a batch of tokens. Our experiments indicated that early in training, unused hidden units may still have the potential to activate. However, later in training, if a hidden unit remains unused, it is likely to be effectively dropped by the model. By selectively masking inactive hidden units during training, we observed no significant impact on model accuracy, suggesting that unused dimensions could potentially be excluded from later stages of training to exploit batch-level sparsity. This finding opens up possibilities for optimizing ReLU models by leveraging emergent sparsity without sacrificing performance. Section Summary. In this section, we focus on a 6-layer decoder-only transformer model with a hidden dimension size of 32,768 and ReLU MLP nonlinearity, trained on C4 next token prediction using LeCun normal initialization for dense kernels within the MLPs and an Atom W optimizer with a cosine decay learning rate schedule. We explore how different layers in the network use varying numbers of hidden units during training, with the first layer consistently using the fewest and the final layer using the most. Additionally, we investigate the evolution of sparsity during training, observing that early layers tend to become sparse first, while the first layer gradually uses its hidden units more frequently over time, suggesting that unused hidden units in early training stages may not necessarily be dead, but could be removed later without impacting model performance. Section: How do neurons die? In this section, we explore how neurons die and the concept of feature specificity in neural networks. We have observed that the traditional understanding of neuron death as a random or accidental process may not hold true in all cases. Even if a neuron appears dead within a batch, it can still be activated during the training process, challenging the idea of permanent neuron death. We also introduce the concept of feature specificity, which considers two extreme ways features can be constructed in neural networks: continuous shared subspace and binary representation. The former involves informative values along all dimensions, while the latter uses binary values to represent information. As we move higher in the network layers, features tend to shift from a continuous to a binary model, impacting the number of hidden units used per token. The sparsity observed in neural networks raises questions about the model's usable capacity. Despite batch-level sparsity, the model may not effectively utilize all available dimensions. When we constrained each layer to the number of hidden units used at convergence, expecting less sparsity, we found that the model still exhibited similar sparsity levels. This suggests that each layer has a specific subset of initialization space for effective learning, and reducing the total hidden dimensions can limit this capacity. Overall, our findings indicate that sparsity in neural networks is not simply a random occurrence but may be influenced by the model's construction of feature spaces. Further research in this area could provide valuable insights into optimizing neural network performance. Section Summary. In this section, we challenge the conventional understanding of neuron death in neural networks, suggesting that it is not a random or accidental process but rather driven by the model's construction of certain feature spaces. We introduce the concept of feature specificity, illustrating how features in neural networks can shift from a continuous shared subspace to a binary representation as we move higher in the network layers. Additionally, we explore how batch-level sparsity in neural networks may indicate a bottleneck in capacity allocation across layers, impacting model performance and suggesting that each layer has a specific subset of initialization space it effectively utilizes for learning features. Section: Sensitivity to hyperparameters. In this section, we focused on a single case study model to delve deeper into its examination. Our aim was to understand how the patterns of sparsity generalize across various hyperparameter settings. Plots illustrating the behavior during training for all experiments can be found in the appendix. When it comes to the sensitivity to the learning rate, our optimizer follows a specific structure with a warm-up period of 5,000 steps leading up to a peak learning rate, followed by cosine decay. We observed how the hidden unit usage per batch of a 6-layer model changes with different peak learning rates. Notably, the standard setting of 3E3 showed the best performance as it was chosen through hyperparameter search. Across different learning rates, some consistent patterns emerged. Layer 0 consistently had fewer dimensions per batch compared to other layers, while the top 2 layers used the most dimensions, with the final layer using the most dimensions except for one case where layer 4 used slightly more. Overall, the sparsity levels decreased as the peak learning rate decreased, especially the extreme sparsity in layer 0. Regarding the sensitivity to hidden dimension, we found that wider models generally exhibited higher levels of sparsity. This trend was consistent for both hidden units used per token and hidden units used per batch. This suggests that there is a minimum number of hidden units required for good performance, beyond which additional hidden units provide diminishing returns. Exploring the sensitivity to model depth, we trained models with 6, 10, and 14 layers, all with a hidden dimension of 16,384. Unlike the width variation, we did not observe a clear trend in hidden units used per token with increasing depth. However, the hidden units used per batch tended to increase in deeper models. This could be due to the creation of new layers that behave similarly to the later layers of a shallower model. While some layers in deeper models showed behavior similar to layer 0 in using a small fraction of hidden units per batch, suggesting the value of additional instances of different layer types as models get deeper. The primary limitations of our work stem from focusing solely on small models and ReLU activation functions, which may limit the direct applicability to larger modern models. The choice of small models was due to constraints on computational resources, while the use of ReLUs was motivated by their induction of hard sparsity for easier study. We hope that future research can identify ways to effectively utilize capacity across various activation functions. In related work, previous studies have examined sparsity dynamics in encoder-decoder models, focusing on T5. We expanded on this by not only looking at sparsity in fully trained models but also studying how sparsity evolves during training. Additionally, we took a comprehensive view of sparsity at different levels: token, sequence, and batch. Other related works have explored inducing structured sparsity beyond training-induced sparsity, showing potential for improving model efficiency without sacrificing performance.